Log on, tune in, find out. Another good idea from Cambridge.
Second lecture, and I'm very pleased to introduce Eric Friedlander from the University of Southern California. He'll tell us about his investigations of KD modules using nilpotent operators.
Thank you for having me. I thank the organizers for inviting me to talk. This is in some sense very elementary representation theory, and just for example, John Carlson, Andre Suslin, and I have just written a paper, and it's a fairly long and complicated paper, and it's about the representation theory of Z mod P cross Z mod P. So I just sort of set the stage for the fact that this is elementary in some sense. And I'd like to mention, this work goes back, it goes back to work of Dan Quillen, whose name I'd like to mention. And then many, many years ago, Brian Parshall and I did some things which leads into what we're doing. And then also there was some work with Chris Bendel. But what I'll be talking about is joint work that's ongoing. Some of the things I'll say are either in preprint form or not written up yet, with John Carlson, Julia Petsova, and Andre Suslin. And I'll probably be quite sloppy about identifying who did what, so just think that there is many people such as those in the background. And I thought I'd be a little bit philosophical about what we're trying to do. This started with work of Quillen. And Quillen was interested in the cohomology of a finite group. And by cohomology, we just mean X star KG K K. So we fix a field K, field of characteristic P. And one can say, for whatever reasons, be interested in the cohomology of groups. And a friend of mine years ago asked me why be interested in the cohomology of groups. And this has bothered me for some time. And maybe this talk will answer some of that, so this philosophical question. But in any event, Quillen looked at this, and he proved a remarkable theorem. Quillen looked at I guess he looked at the maximal ideal spectrum, but let's not worry about that. We'll think of it as the prime ideal spectrum of the cohomology of this arbitrary finite group. And certainly at the time, very few cohomology computations were known. And Quillen told us what this is for absolutely any finite group. You can write it, I'll write it this way, as some sort of co-limit over a category of, not very large category at all, of elementary abelian P groups inside G. And the cohomology of these, E is elementary abelian, isomorphic is Z mod P to be across itself R times for some R. And these cohomology groups, these spectra, are just, if E has rank R, this is just affine R space. So it's a very simple geometry, and he just answered what this geometric space was associated to cohomology. Now there's a little bit of funny business here. What we usually do is look at the even dimensional part to make this a commutative algebra. So we're looking at a finite generated commutative K algebra and looking at its spectrum. And this ignores completely nilpotent elements in the cohomology, so this does not tell us what the cohomology is in any degree, but it certainly gives us a geometric invariant of G. And this is the beginnings of what I'm about to talk about. Now, I haven't observed. Do I have to be as tall as Henning, or do I jump? Maybe I jump. So this is this sort of background for what we're doing is cohomology, but I won't be mentioning cohomology very much. I'm interested in studying representations of finite group schemes. So in particular, finite groups, and in particular, Z mod P cross Z mod P. And what does cohomology have to do with this? Well, what we're really going to be doing is study the effect or the action of nilpotent operators. And you'll see that this has to do with cohomology. So associated to a G, a finite group scheme, such as a finite group, we'll associate, it's actually a scheme, but anyway, we'll think of it as a topological space. And I'll call this the prime, maybe we'll call it the prime spectrum or something. So this will be the governing space. And in the case of a finite group, this will just be proj of this graded algebra of the cohomology. And we'll be looking at structures associated to this space. And in some sense, this space plays the role of, say, G mod B, something like that, for studying the effects of nilpotent operators. So I want to introduce the space and look at various guises to it. And so my task is to introduce this and to describe invariants of representations of G, and we'll call these are just called KG modules. And we could describe these as geometric. And they'll be of two sorts. There'll be local invariants, by which I mean they vary from point to point in this space, this governing space. And some will be global invariants, by which I mean that it'll take into account this is a projective algebraic variety. So this is a very long-term program, and as I mentioned, some of us just wrote this complicated paper on Z mod P cross Z mod P. We're never going to get anywhere near finishing what we're trying to do, but let me try and describe some of that. And I guess I should mention something about nilpotent operators just briefly, just still in the stage of philosophy. What we're interested in is, well, what this can handle to some extent or investigate to some extent are not the irreducible modules at all, but cohomology is useful for studying extensions. So what we'll be doing is looking, in some sense, trying to understand indecomposable modules over these guys. And the nilpotent elements seem to play a role similar to, in terms of listing indecomposables or whatever, as do semi-simple elements or actions of tori in other contexts. So that's vague, but maybe we'll see a little more of that later. So let me briefly talk about this governing space or variety that we're working with. And maybe what I should first do is say what a finite group scheme is. Well, I'd rather not. I'd rather say examples. So we have a finite groups. And what we're really interested, we'll be looking at the cohomology and then the module theory for the group algebra of a finite group scheme. So it's easier for me to tell you what the group algebra of a finite group scheme is. So the next case would be p-restricted Lie algebras. Which is how Brian Partial and I got involved in this. And the KG in this case is the p-restricted enveloping algebra. And then the case I'm probably most interested in are what are called Frobenius kernels. We take a some sort of algebraic group, affine algebraic group, and then we look at the kernel of Frobenius on this, or maybe some number of times, r times on this algebraic group. If it's not defined over Fp, then it doesn't quite go to, it's not quite an endomorphism. And this too is an example of a finite group scheme, a very interesting example, as I hope I'll convince you. This is often called G sub R, which is Rg. And to write down what its group algebra is, one can do it, at least with generation relations. It's not commutative, but it's easier to think of this as a functor. And so sometimes we look at finite group schemes or all of this structure in different ways as a functor, representable functor on finite dimensional K algebras, finitely generated K algebras. GR takes a K algebra A to the kernel of G evaluated on A, and then apply the Frobenius R times to G evaluated at A. So it's actually easier to see. It's a group valued functor on finite dimensional K algebras. Representable, all of these are representable by finite dimensional commutative. They're represented by finite dimensional commutative algebras. The group algebra in every case is a finite dimensional co-commutative Hopf algebra. Okay, these are the structures we're interested in, but we could just focus on elementary ones and don't have to worry too much about how complicated they are. And then we have, in any of these contexts, we can take the X algebra and we can think of the proj or the cohomology. So there's another way to view this, and it's due to Suslin, myself, and Chris Bendel. So if G looks like one of these infinitesimal groups, well, if it's infinitesimal, if it looks like one of these Frobenius kernels, for example, then we have a natural homeomorphism from relating the cohomology, the spectrum of the cohomology, and another space, which is much more geometric. This is homeomorphic, related by algebraic maps, which are induce bijections on the Zariski spaces, homeomorphic to the variety of one parameter subgroups. So if G has, well, I'll call this V of G, a variety of one-parameter subgroups. This is infinitesimal of some height, let's say R, and we look at one-parameter subgroups, which I'll explain in a moment, of height R into G. So before I even explain what this means, let me, a special case. If G is equal to G sub 1, which corresponds to the Lie algebra of our algebraic group G, then this says that the spectrum of the cohomology is homeomorphic to the p nilpotent cone of G. That's what these variety of one-parameter subgroups, in this case, it's just the p nilpotent cone of G. So we immediately see that geometry appears. So in Quillen's computation, there's the answer. The geometry is quite simple. We have these affine spaces, and they're patched together, and there's some automorphism, so we look at some sort of like orbit folds of affine spaces patched together. Here we're getting interesting geometry even in the case of height 1, and the geometry gets more interesting. And so what we're interested in is taking proj of this. So we'll take our pi of G, that's our underlying space that will work throughout the lecture. Our pi of G in general will be, for an infinitesimal group scheme, it'll be the proj. Well, the way you write this, this is a homogeneous variety. It's defined as a scheme, and it's with a coordinate algebra K of V of G. And so I just want proj of that, which is called proj of K of V of G. So here's the governing space again, this pi spectrum, which is the same as this, but more geometrically described in the case of one of these infinitesimal group schemes. So what are these one-parameter subgroups, and how does this help us understand something about what's going on? It certainly suggests that there's some geometry and maybe some depth to the study of cohomology. So maybe it's simplest to talk about one-parameter subgroups of height, some height R, and that they will be just maps of group schemes. This is from GA sub R to, this is the Frobenius kernel of applying F to the R on the additive group. Maps of group schemes into our group G. We look at all of these. We can make this a functor on commutative K algebras, so it's representable by some finitely generated commutative K algebra. We look at its spectrum, that's V of G, that's homeomorphic to the cohomology, and we look at proj. So just as an example, if we look at a classical group like the general linear group, and if we look at the rth infinitesimal kernel, so we look at G equals GLNR, which is the kernel of rth Frobenius from GLN to GLN. The way you should think of this is an infinitesimal neighborhood of the identity on this algebraic variety. And the representation theory, the rational representation theory of GLN, is perfectly reflected by the family of these infinitesimal neighborhoods. So in this case, V of G the one-parameter subgroups. What is this variety of one-parameter subgroups? This is equal to the variety of R tuples, that's this R tuples of pairwise commuting p-nilpotent elements M by M matrices. So in the special case that R is 1, we just get the p-nilpotent cone. This result about p-nilpotent cone originally came up in work first of Brian Parshall and myself and Jens Janssen, but there was some condition on p, and it took this work to eliminate the condition on p. So in the case of infinitesimal group schemes, our controlling space for our p-nilpotent operators will be this proj of one-parameter subgroups, or we could just go back to cohomology. Well, there's a third version of this, which is the way I actually think about these things now. And that's due to Julia Petsova and myself. So we introduce a new space, and I'll still use pi of g for this. Now g is an arbitrary finite group scheme. And we show that proj of the cohomology is isomorphic as schemes over K. K is an arbitrary field of characteristic P. This is isomorphic schemes to some scheme that's, I'll just write it this way, equivalence classes of flat maps from Ku mod u to the p to Kg, G is our particular guy, where K over K is a field extension. If we were working over an algebraically closed field, and if we didn't care about the scheme structure, we could just take we could just stick with the ground field, little k, but it's useful to do this. And these flat maps, they have to satisfy the condition that they factor through a unipotent abelian subgroup scheme, which doesn't have to be defined over K. So this turns out to be very useful because we're seeing here U is a p-nilpotent operator sitting inside the group algebra. So when we have modules for Kg, we will have actions of elements, p-nilpotent elements, acting on those modules. So here we can see p-nilpotent operators. Okay, so we have now 3 different forms of our governing space pi of g. Let's now consider representations. Maybe I should say, just if we had, maybe my favorite example, the one I've spent the most time on, is G equals, I've mentioned it several times, ZP cross ZP. Then just to make life concrete, pi of G is the projective line. If this was ZP cross R, pi of G is P to the R minus 1. So now let M be a finite dimensional KG module. As always, G is a finite group scheme. And the finite dimensionality plays a role some of the time, but it's actually amusing to observe that the approach of thinking about cohomology or the effects of cohomology through this space, one can often drop the finite dimensionality assumption and prove theorems that were once known only for finite dimensional modules. But let's assume M is a finite dimensional module. Then there's a construction called the support variety. Of M, and this is going to be an example of what I think of as something that happens locally on pi of G. So for the purposes of this talk, I'll define it as follows. So we have our group G in our topological space pi of G. It's actually a scheme. And we're going to take a closed subvariety inside pi of G. And this subvariety will be the collection of equivalence classes of these maps. Let's call this alpha. So these are just flat maps that happen to factor through something abelian. And we look at these maps, and I haven't told you the equivalence relation. Maybe I should, but I won't at the moment. So we look at these maps such that a representative of the map has the property that alpha upper star of M is not projective. As a K, U, to U, P module. So to be a little more careful in notation, since I base change from little k to big K, I usually put the big K, make it explicit like this, and I have to base change the M, but maybe I'll forget all that now and just from now on not be explicit about the field I'm working. So this is a specific, at every point in this governing space, every homogeneous prime ideal of the cohomology spectrum, or every one of these points, or every one parameter subgroup, I just ask yes or no, is the module restricted to that little point? Thinking of it with this nilpotent operator that varies from point to point, is that module projective or not? So this support variety has lots of nice properties. You've probably seen these support varieties before, and I'll just mention a couple of properties that just briefly. M is projective if and only if pi GM is empty. Pi G of M plus N is the union. Pi G M tensor N is the intersection. Pi G of a Heller shift is the same as pi G of M. And then this is only this one invariant, the support variety, has interesting properties for the stable module category, the triangulated category structure of stable modules. But what I'm about to do is introduce many more finer invariants which don't have such good properties, so I just write these down to emphasize they do have good properties. But here's a major objection to this pi G of M. Pi G of M is the whole space pi of G whenever P does not divide the dimension of M. So you might say it's not the ideal invariant, but it's certainly a very interesting invariant. So we have this governing space, this prime spectrum pi g, and from point to point we have these points are equivalence classes of nilpotent operators, and this support variety is just at each point it asks, is the module or is it not? Does it appear projective or not? So we can think of, here's our projective algebraic variety, almost always singular. And above it we have some bundle, or maybe not bundle, but coherent sheaf associated to M, and above a point we look at the fiber there and ask, is this a projective module, or free if you want, for the associated operator U, which varies from point to point. Now, it seems a remarkable fact, and it took a great long time to prove. This is a theorem of Petzova, Suslin, and myself, that one can extract more information out of this than just yes or no, is the module projective. So, theorem. At a generic point, so here we do need to be a little, think of these as schemes and allow base change. At a generic point of pi of g, the Jordan type of a given M is independent of the representative alpha of that point. So what this says is, if we have, for example, a finite group, and we construct this pi space, this pi spectrum, and in a finite group, the generic points correspond to the conjugacy classes of maximal elementary abelian P groups. At every conjugacy class of maximal elementary abelian P groups, we have a new invariant, the Jordan type of the module at that point. And moreover, at any point at which, for some representative, alpha upper star M has maximal Jordan type, this type is independent of representative. So let me just tell you what I mean. I mean something very elementary by Jordan type. So what we're doing is beginning to study modules by restricting to this very small algebra. Actually, we're allowing the field to grow, but it doesn't matter. So this is, if you will, isomorphic to the group algebra of Z mod P. And we know exactly what the module theory of this looks like. Any finite dimensional module is isomorphic to the direct sum from I equals 1 to P of Ku mod U to the I a bunch of times. And I'll write this as summation AI times I. And I'll think of this as the Jordan type. So Jordan type, if you will, is just the, you can either think of it as the Jordan form of this operator, U, the image of this map, or you can think of it as just the isomorphism class of the module pulled back to this. And so this says, not simply is it the case that you can say whether or not the module is projective, it's projective if and only if all AIs are 0 except AP. But you can read off the entire Jordan type. So already we're getting more information about modules by looking at their Jordan type, and we can see that that's an invariant of the module and the group involved at generic points and at maximal types. So this is the sort of information that we're pleased to have. So we get we can sort of characterize and distinguish various modules by looking at Jordan types at generic points. Now, knowing that these, the Jordan type at generic points and maximal points are well defined gives us lots of new games to play. But before I do this, a warning. At this is as strong as you can get. If you take a random point in our control space pi g, which is an equivalence class of maps, and if you take two different representatives, almost surely you'll get different Jordan types. They have really nothing to do with each other. So I'll just give you an example, and usually my examples come from C mod P cross C mod P. This is our KG in this example. Okay, so what we can do is we could look at the module M. Why don't we can take almost anything. KXY modulo, let's say, x squared, maybe x minus y squared. So in this case, then we have these, what we call pi points, these representatives of points in our pi spectrum. They're going to kx, y modulo, x to the p, y to the p. And we're supposed to, so here's an alpha, and we pull back m to that. And now, the way the equivalence class works, u going to x and u going to x minus y squared, these are equivalent. But the Jordan types maybe I should put beta here, two different ones. Jordan types are very different. And the reason is I didn't define the equivalence relation. Two maps are said to be equivalent if they give the same yes-no answer for any module, finite dimensional module M. Yes or no, when you pull back, you get projective. It has nothing to do with Jordan type. It just has to do with projectivity. So to know that the Jordan type can be recognized in certain circumstances is not a formality. Okay, but with that warning, we do have these well-defined Jordan types. Let's see, I couldn't phrase it quite like that, but certainly the support variety says yes, no, whether, yeah. So it's very, very closely related to the, yeah. So one thing John Carlson, and then John Carlson, Julia Petzova, and I have been playing with are what we call modules of constant Jordan type. We're still in the local invariance, but and this paper with Andrei Suslin was trying to give as much information as we could about modules of constant Jordan type just for ZP cross ZP. And we could say some things, but not. We certainly don't understand them. But let me just describe. This is a whole new class of modules. Well, I guess it hadn't been identified before, but it's really quite a fascinating class. And you could only see it from this point of view. So M is a module of constant Jordan type. If for all pi points, that's these maps alpha, Ku mod Up into the group algebra Kg, alpha upper star M, and I should do a base change, has the same Jordan type. Now, by that theorem, one only has to check at all equivalence classes. You don't have to check for every representative of every equivalence class. Now, it turns out there are myriads of these. I mean, for any finite group scheme, we can construct ones using cohomology. We can, every endotrivial module is one of these. We can trace them along on quivers. They're certainly not every module. Most modules have Jordan type that varies from point to point. But these modules are really very interesting, and just one thing we do is we classify, what shall I say, cyclic modules. This was actually quite hard. Cyclic modules of constant Jordan type for ZP cross ZP. Another thing we do is we give a functor from modules to modules of constant Jordan type. So to every module constant Jordan type, we find a maximal submodule. For every finite dimensional module, we find a maximal submodule that has constant Jordan type. So these are an amusing class of modules. So I just say endotrivial modules. There are many, many more of these than endotrivial modules. We essentially know that they constitute a wild category, but we don't have a sort of formal proof of this. So then I want to describe how one can also think of these nilpotent operators more globally. What we've done so far is associate a space to the group, this pi space, and then this pi space, at every point, there's a nilpotent operator. It's really equivalence class of nilpotent operators. And then we can study modules by looking point by point at this nilpotent operator. And now I want to look globally over the whole space and look at the operator. So what's a global invariant? Well, what sort of failure? I don't know how to finish the sentence. I started out with incorrect English, and I'm going to have to end with incorrect English. What sort of failure does local study entail, whatever that means? Sorry about that sentence. What I have in mind is if I take a module M, and if I take its linear dual, these have the same Jordan type at every pi point. So in my thinking, they have the same local Jordan type. And that's because if you take a module and its dual, it's going to have the same Jordan type. There are various other examples. Of course, we're talking about wild categories, so stable module category or whatever, and we can't possibly detect all modules with these sort of techniques, but we're trying to detect more. And another, these global invariants will distinguish in some cases. If M is projective, that's projective as a KG module, then the local type is completely uninteresting. It just gives you, just says the support variety is empty. It just says that at every point it's a free module of, say, the same rank. So this global invariance I'm going to describe, at least in certain cases, will distinguish a module and its dual and will distinguish projective modules. And we've moved away from cohomology, but what we are doing is keeping this control space pi of g. So in some sense, we still are grounded in cohomology, and much of what has been what I've described has the background or cohomological computations. So how could we get global invariance? The idea is pi of g, this is a projective algebraic variety. So if we take a G module M, we can get a really exciting module over this pi of G. We'll just take M and tensor it with the structure sheaf. So this guy, not very interesting at all, is a free module, free O pi G module. So far we've done nothing at all. We have this algebraic variety, and we take a direct sum of copies of the structure sheet. This is tensor over the field. This is finite dimensional. We take a direct sum. We just have this free, coherent O pi G module. But now we have this action of these nilpotent operators. And so what I'm next going to introduce is how on this free, uninteresting module, we can get an endomorphism. It's not quite an endomorphism of this free module to itself, and start looking at kernels, which will give us non-trivial bundles. And so what we'll do, or not do in the next 10 minutes, and this is work that is done in joint work with Julia Petsova. What we introduce is, you might call it a universal p-nilpotent operator. And it turns out to be sufficiently graded that we can, in this context, we can give a map from M tensor O of G to, let's say, O pi G to M tensor O pi of G. And we'll consider kernels of this operator for various J. So these guys are going to be global invariants. And this theta G, what is this? I don't know how much you can picture this. My training is as an algebraic geometer. Over pi of G, point by point, we have this little p-nilpotent operator. This theta G is this p-nilpotent operator patched together over the whole space. So fiber by fiber, it specializes to our little u, but it's varying from point to point. So if we base change from pi of g to one particular point, we'll just get that operator u. So this incorporates what I think of as the entire local Jordan type of the module, where this actually turns out to be a very complicated operator theta g. Now, some of what I've said here is too simplistic, and I want to first do an example, and then just very briefly an example, and then mention why it's simplistic, and then derive some corollaries from this point of view of this, taking these global invariants. So, as an example of what we're doing, and this is a funny example. I'm going to say that this does not work. We don't know how to do this for finite groups. We only know how to do this for infinitesimal group schemes. But in the one case where, the one and only case where a finite group is basically equivalent to an infinitesimal group scheme is E is an elementary billion P group. Because then it looks like it has the same group algebra as GA sub 1 across R. So it's infinitesimal group scheme. But in this case, our universal operator is, so what it looks like, our operator, we have KE tensor, the coordinate algebra of, well, we're in the affine case, so it's the coordinate algebra of, let's say, V of G. So for KE, we know what this looks like. This looks like K, I'll index it this way, R minus 1, modulo UI to the P, just the group algebra of PBR. And then the affine variety associated with this is affine R space. So this is tensor K x0 up to x R minus 1, divide out by nothing, it's affine space. And our operator, our affine operator in this case, you can guess what this is. This is simply summation UI tensor xi. And so we have this operator on bundles, and it passes to projective space, or on modules, and it passes to projective space. This operator gets extremely complicated. One example that I like is if we look at GA sub R. This also has group algebra that's just the same. It has group algebra isomorphic to this one or that. But the operator has a grading on it, and this gives bundles on weighted projective spaces, which are singular, by the way. And that arises because this operator is no longer some simple linear thing. It has all sorts of weights in it. Okay, so that's an example of what the operator is, and now let me tell you why the operator, it's a little complicated to construct, and it doesn't exist. We don't see how to do this for finite groups, although I have some ideas. But at the moment, it works only when pi of g can be represented as proj of one-parameter subgroups. Points are one-parameter subgroups. And this is because there's this equivalence relation. I keep thinking there should be some stacked version of this which can get around this equivalence relation. But for a finite group, we're looking at equivalence classes of these pi points, these flat maps, and you have to choose a representative. So here, in some sense, this is giving us a representative point by point. And there doesn't seem to be any way to do this for finite groups. But for these infinitesimal group schemes, there is a well-defined choice of representative of each one. You're using the Hopf algebra structure, which I haven't been in many of these cases. We look at a one-parameter subgroup as this. It's given by very specifically, not just an algebra map, but by a Hopf algebra map. So there turns out to be canonical representatives of these pi points, and it enables us to fit these together. So what do we do? Well, we now have the space and we have this free module, which is totally uninteresting. But we also have this endomorphism, P nilpotent endomorphism, theta G. We put a tilde on it when we look at the projectivized version. And now, for example, if M has constant Jordan type, each of the kernels for J, 1 less or equal to J, well, the P iterate is just the zero operator. Each kernel is a vector bundle. Indeed, I guess I don't have time to do this, but what we need to say is that if M has constant J type, not just the entire Jordan type being constant, that also makes sense. All that we've done makes sense by focusing on a single power of the operator. If there's constant J type, then this bundle for given J is a vector bundle. We have many examples of modules which have constant J type for one J but not for another J. So here's just one amusing example. That shows something's going on, but it's the only example I can do like this. So the example ends up working on P1, not surprising. I'll look at the case that G is associated to SL2. So I write that underline for the group scheme. So it's group algebra is the restricted enveloping algebra of SL2. Then what we show, Julia Petzova and I show, that if you look at the Grothendieck group of projective modules for this finite dimensional algebra, this Grothendieck group of G. So these are projective modules on the side. Well, to each projective module, a projective module certainly has constant Jordan type. Its local type is uninteresting, but it has constant Jordan type. But for each of those, we can take this bundle, and we'll do it for all J. And the controlling space for this SL2 is also P1, which is why we can do a computation. So now what we'll look at is K naught in the terms of equivalent K naught of an algebraic variety, K naught of P1. And we look at the reduced K naught, but anyway, we look at K naught of P1, and we have P different bundles. These are taking the kernel of the first iterate, the first power, the second power, etc. And this is a rational isomorphism. After we tensor with the rationals. So in particular, taking these bundles distinguishes different minimal projective bundles. So this invariant is far different from support varieties. We're distinguishing projective modules using this. Now my dream in all this, so maybe I'll put this at the end, and maybe say it as a challenge or something. So when we first started developing this, I was really quite excited, but I haven't been able to push this through at all. But the dream is, what this is doing is we're associating, this isn't a dream, we've got this part, associating to certain quite explicit KG modules vector bundles on pi of g. Now, pi of g is a very interesting variety. Mind you, it looks like something like R tuples of pairwise commuting matrices or something. Highly singular, but an interesting variety. So we associate these, we can say modules of constant Jordan type. We can write down just huge families of these very explicitly. And to each of those, we get families of bundles on this. And we even know when a module of constant Jordan type, for example, gives you the trivial bundle. It's very rare. So the dream is, associating this, we get new and interesting vector bundles. Well, I'm sure this is true. I'm sure that what we're doing is producing, with these explicit KG modules, very interesting vector bundles, but I don't know how to measure them. The problem is, if one looks in algebraic K-theory, we know very little about the algebraic K-theory of varieties which are not smooth. And almost none of these are, almost all of these are singular varieties, including these weighted projective spaces that I mentioned. So we're obtaining bundles, but I don't know how to measure how interesting they are. The only thing I know how to measure is that in some cases I can say that some of them are different, but I don't have a group that I can say, look, they're different in this group because I don't know what it is. So producing something like that. So this does produce interesting bundles. And just for example, one specific dream is produce new bundles on projective spaces. Now that's at least a smooth variety, and that goes back all the way to elementary abelian P groups. So Dave Benson and Julia Petsova thought something about this, and they can realize, you may know that we don't know whether there's an, I guess, a rank 2 indecomposable vector bundle on P2. There are all sorts of things that aren't known about vector bundles on projective spaces. So here we have explicit representations, and maybe we can produce vector bundles. Okay, thank you very much.
Thank you. Questions? Comments?
Are there any cases where you might dream to get sufficiently many invariants to actually distinguish indecomposable representations from each other?
So my whole motivation with this whole program was people explained to me that everything, all these group algebras have wild representation type. So that's a red flag. I thought, they said, that means you can't classify. So I thought, okay, let's classify. So I'm not actually sure. I mean, what's happening is we're getting invariants like all curves in some place. I don't know whether there are enough such things that it's logically possible that, when you look at all the possible subvarieties inside something and you put all this decorated structure, whether that's enough to capture the wildness or not. But surely that's the motivation in some sense, to get finer and finer invariants to be able to distinguish as much as possible. But theoretically, I'm not sure.
But indecomposable, so constant Jordan types.
Well, John and I have essentially proved that that's a wild category.
Still not.
Yeah. And we show that it's just an enormous, even for ZP cross ZP, we show how, we just produce these huge families that, so it looks very wild.
Do you require that your vector bundles over singular varieties have constant rank?
Sure, let's assume the variety is connected, yes. So then it becomes
Okay, so it is.
constant rank, yeah.
In the case of Frobenius kernels of
Yeah.
semi-simple groups,
Yeah.
what how do these Jordan type or constant Jordan type? What does it mean for? And do we have classes of modules described other ways which
No.
you can put into these, so they're completely perpendicular to anything else?
As far as I know, well, all endo-trivial, there are examples, but I mean, I don't know, I don't know how to translate what it means. I mean, I know how to construct them, even for those guys, for arbitrary infinitesimal kernel. I know how, using cohomology techniques, I know how to construct, and then using quivers, I know how to get very elaborate modules of constant Jordan type. But I don't know any way to characterize it. I mean, it's this point by point Jordan type. Yeah, I don't know.
Let's thank the speaker again.